So we've seen that linear systems can be consistent or inconsistent. Consistent meaning that they have at least one solution, and inconsistent meaning that no solution exists. So keeping those definitions in mind, we want to talk about the types of solutions that we're going to see for a given system of linear equations. So the first type of solution to a linear system is exactly one solution. We could even say exactly one unique solution. So if a linear system has exactly one solution, the system is consistent. And now the linear equations that make up this system are called independent equations. So the equations in our system are independent of each other. They are unique or distinct equations. So let's look at an illustration of such a linear system. So let's say that we are given the system x sub 1 plus x sub 2 is equal to positive 1. And equation 2 is defined as minus x sub 1 plus x sub 2 is equal to minus 1. So here's a beautiful system of linear equations. And since we want to think about this graphically, I'm going to rewrite this in an equivalent form, solving for x sub 2 in each case. So we have x sub 2 is equal to minus x sub 1 plus 1. And equation 2 becomes x sub 2 is equal to positive x sub 1 minus 1. And you don't have to rewrite it like this. I like to rewrite it into this format so I recognize the equation that we know from calculus. So this first equation would be y is equal to minus x plus 1. And our second equation here is simply y is equal to positive x minus 1. So let's go ahead and sketch this illustration. So if you have graphing paper, I encourage you to use it. Otherwise, just be sure to label your scales. This is not art class, so as long as you label, we are all set. Alrighty, so looking at equation 1 here, we can see that we have a y-intercept at positive 1 and a x-intercept at positive 1 as well. So to sketch this line, we simply draw a smooth curve passing through those 2 points. So here is our equation 1, or x sub 1 plus x sub 2 is equal to positive 1. Now equation 2 has a y-intercept at negative 1 and an x-intercept at positive 1. So again, very similarly, to sketch this line, we draw a smooth curve passing through those 2 points. So here is equation 2, which was given to us originally as minus x sub 1 plus x sub 2 is equal to negative 1. So looking at this graph here, we can confirm and see that this system has one unique solution. But we have a single solution here at the ordered pair 1, 0. So I want you to note, in terms of writing the solution as your final answer, we would write this as a vector. So the solution to our system is written as the vector x, where vector x is in R2. So we can even define our vector x as a column vector. We have the x sub 1 coordinate and the x sub 2 coordinate, where x sub 1 here is positive 1 and x sub 2, or y, is 0. So we have two distinct or two independent equations with one unique solution, one intersection point. So that's our first case. What about the other two? So the second type of solution to a linear system that we need to consider is the case where there are no solutions. So we say that systems with no solutions are inconsistent systems. So again, systems with no solutions are inconsistent. So if we're thinking about a linear system here in R2, we say that the linear equations that make up this inconsistent system are independent of each other. So the linear equations that define this system are independent or distinct. So let's look at an illustration of this in R2. So here we are given this beautiful system, minus x sub 1 plus x sub 2 equals 0. So there is equation number 1. And our second equation is minus x sub 1 plus x sub 2 equals 2. And rewriting this system in an equivalent form, for graphing, we can say our first equation is x sub 2 equals x sub 1. So our standard diagonal line. And the second equation can be rewritten as x sub 2 is equal to x sub 1 plus 2. So let's think about what these two linear equations look like graphically. So equation number 1 is our standard diagonal line. So we have that x and y intercept at the origin, and we'll draw a straight line through this point. So here we go. Here is equation number 1, given to us as minus x sub 1 plus x sub 2 is equal to 0. And now our second equation is simply the same diagonal line, but shifted up 2 units. So we can think of this as y is equal to x plus 2. So we have that y-intercept at positive 2 and a x-intercept here at negative 2. So notice when we go ahead and draw the line connecting these points, we see we have parallel lines. So parallel lines are an example of an inconsistent system with independent equations and no solution. And our third and final case is the case where a linear system has infinitely many solutions. So systems with infinitely many solutions are consistent systems. So our system is consistent. And now again, thinking specifically for an example in R2, the linear equations that define this system are dependent here. So the linear equations are dependent on each other. So to better understand what we mean, let's think about an example. So here we have the linear system 2x sub 1 minus x sub 2 equals 3. So there's our first equation. And equation 2 is 3 times x sub 2 is equal to 6x sub 1 minus 9. So let's reorder this so it looks the same. So with equation 1 here, I'm going to rewrite this in a graphing format and say that this is 2x sub 1 minus 3 is equal to x sub 2. And then notice with our second equation that we have a greatest common factor of 3. So if we divide both sides of the equation, 2 by 3, we end up with x sub 2 is equal to 2x times x sub 1 minus 3. So what are you noticing about these two lines? They're the same. These lines are the same. Although we have the terms on the different sides, they are in fact the same. So when we graph this, we have a y-intercept at negative 3 and a x-intercept here at 3/2, so 1.5. And again, drawing that smooth curve to connect these 2 points, we have the graph of our system. So there's only one line on our graph. So equation 1 is equal to equation 2. So we can see how these lines depend on each other. And we can see also how we have infinitely many solutions. And we say that we have infinitely many solutions because every point on the line is a solution point. So every point or every ordered pair on the line is considered a intersection or a solution point.